In this video, I'm going to be talking about how to do some different pulley problems, which are also known as Atwood machines. So we have a vertical pulley over here, and then we also have a pulley pulling an object on a ramp. If you wanted to see a pulley problem with an object being pulled along a flat surface at a 90-degree angle, then click on the link above. All right, so the first way to start off the problem solving process with these is to always draw your force diagram first. So I'm going to go ahead and do that and then proceed from there. All right, so I drew the forces on each of my objects. I called these FGs FG8 and FG5, so I knew which force of gravity was which. And then I also did the same with the FTs. So you want to do two more things when working with a pulley problem. Number one, you want to identify which direction is positive and negative. So all along the string or the rope on an Atwood machine, you have to identify which way is positive and which is negative. So I'm going to say that because this is 8 kilograms and the rope is going to be pulled up and over this way and then downwards, that everywhere along this direction, I'm going to consider that positive. Okay, so that's not really typical of a lot of other problems where up is positive and down is negative. So everywhere along this direction of the pulley, I'm going to consider positive, and anything opposite that direction, I'm going to consider it negative. The second thing you want to do with a pulley system is identify what your system is. So my system is the 5 kilogram mass and the 8 kilogram mass together. So I'm basically going to clump up everything in here, and I'm going to say that whole system moving is the thing that I'm going to be analyzing. Now, the reason why that's important is because only forces that are external from your system are to be included in your sum of forces. So these two forces are inside of this green blob that I drew. So they're not going to move the system because there's all kinds of internal forces happening typically, but those are going to have a net force of 0. So we just want to look at the forces that are external. So this FG8 and this FG5. Now, according to the system that I set up, this way is positive. So my FG8 is going to be positive, and anything that goes this way along the pulley is going to be negative. So if I draw my sum of the forces, my sum of the forces are FG8 minus FG5, and that's going to equal M times A. Okay, so I'm going to go ahead and plug in my numbers, plug in my mass, and then solve for my acceleration. All right, so I went ahead and did mg, mass times 9.8, for my 8 kilogram mass minus the mg from my 5 kilogram mass, which left me with a net force of 29.4 newtons. Now, one of the key components to doing a pulley problem or an Atwood machine type problem is taking a look at the whole system. Remember, although we're maybe focused on the 8 kilogram mass moving, there's still the 5 kilogram mass moving along with it, and all of that are within our green system. So our total mass is 13 kilograms. So it's not just the 8 or the 5, it's going to be the 13 in total. So they set that equal to 13 times a, divided both sides by 13, and the acceleration of our entire system is 2.26 meters per second squared. Next, what I'm going to do is I'm going to do the pulley problem over here to the right, which is a lot more complex. So I'm going to start off with the similar steps that I did with this one, as in I'm going to draw my force diagram, identify my system, and then identify which way is positive and negative. All right, so this diagram got pretty complicated. So what I did is I drew all of my forces in red. So I have force of gravity down, normal force up perpendicular from the ramp, force of tension to the left up the ramp. And then for this object over here, we have the force of gravity down, tension up. And then I left out kinetic friction. So the question says, what is the acceleration of the 5 kilogram block if the coefficient of kinetic friction is 0.2? So because it's kinetic friction, I'm going to assume that it's sliding, but I don't know if the object necessarily is going to be sliding this way or if it's going to be sliding down this way. So if it's going to be sliding down the ramp, then friction is going to oppose it by pointing up the ramp. And then if it gets pulled by this object up the ramp, then the kinetic friction is going to be pointing down the ramp. So I'm going to reserve my vector for the kinetic friction for later until I see what's going on. So I made my system both of the masses just like I did with the previous one. And I have a couple forces going on. So what I want to do is I want to look at, again, which forces are external in the system. So I said everything going up and around this way is positive, and anything going back and down is going to be negative. So just like any kind of incline, we want to take a look at forces that aren't necessarily in the X and Y direction, but in the parallel and perpendicular direction. So I have two forces that are perpendicular. So my normal force and what I call the FGY, the Y component of my gravity. And then down this way, I have my FGX pointing down the ramp. And then opposing the system, I have an FG from my 2 kilogram mass. Okay, so what I'm going to do is I'm going to go ahead and set up all the sum of forces in the parallel and perpendicular direction and see what that leaves me with. All right, so what I did is I took my sum of forces in the perpendicular direction, which is just normal force up, and then FGY down. And if you set it up, it's Fn minus FGY equals 0 because there is no movement and definitely no acceleration in the perpendicular direction. So it's safe to say that equals 0. Therefore, the normal force is equal to whatever the FGY is. To find the FGY, all I would do is take the cosine of 25 degrees and then set that equal to FGY over the force of gravity of the 15 kilogram object, which is 15 times 9.8. So 15 times 9.8 is 147 newtons. You multiply both sides by 147 newtons, and then that's how I got the 133.23 newtons for the FGY. Now, looking at the parallel direction, that's where there's a little bit more going on because obviously the block is going to be moving parallel to the ramp in some way. So remember, I held on to which way the kinetic friction was going to go because I wasn't quite sure in the beginning. I saw for my x component similarly how I did this, except I did the sine of 25 degrees because opposite of this 25-degree angle is my FGX. So I set that equal to the FGX again over my hypotenuse, which is the force of gravity for the 15 kilogram mass, so 15 times 9.8, and then multiply both sides by 147 newtons because that's 15 times 9.8. All right, so I got 62.12 for my parallel component down the ramp, and then I have my negative component going up and around the bottom of the pulley resisting it, and that's only mass times the 9.8 of 2 kilograms, so 2 times 9.8 is 19.6, so it definitely looks like there's a lot more force directed down the ramp, which means that if the object is trying to slide down the ramp, then the friction is opposing it in what I call the negative direction along this pulley. So I can subtract then the force of kinetic friction from my FGX. Okay, so the way I'm going to find friction is on the side over here, I would do the coefficient of kinetic friction times normal force, the mu times the normal force, and I found the normal force a little bit early over here. So I'm going to do 0.2 times 133.23, and then I have my force of friction, which comes out to 26.65 newtons. All right, so now I pretty much have everything I need. I completed everything in the perpendicular section early on because there wasn't too much going on there. And then I wanted to wait to see which way friction was going to go. Turns out that it opposes the slide up the ramp against the block because it's sliding downwards. So what I can do is subtract all these numbers to get my net force, set that equal to m times a for my entire system. All right, so I took my FGX, which is my horizontal component from here, subtracted the FG2, and then subtracted the force of kinetic friction, and that left me with a net force of 15.87 newtons, and I set that equal to a mass of 17 kilograms, because remember, it's not just the 15 kilogram mass moving, it's attached to the 2 kilograms, so the total mass of the system is 17 kilograms. So net force equals m times a, divide both sides by the mass, and that left me with an acceleration of 0.93 meters per second squared. So I hope that was helpful in helping you understand, set up, and solve Pulley and Atwood machine problems. Thank you for watching and listening.